Good morning, everybody. Today I'll be talking about little cloud droplets and how they undergo extreme clustering. A lot of what I'll talk about is not particularly about clouds, it's also about any particulate, any droplet laden flow. So, the underlying theme that I'm going to have is caustics. And what is caustics? Like, caustics is another word for extreme clustering. So, by extreme clustering, what I mean is that many particles come into one place, or droplets. I'll be using droplets and particles interchangeably. Droplets or particles come into exactly the same place. Like here in this picture, you see these two droplets are coming at two different velocities and they've come to the exact same spatial location. So this is what we'll call extreme clustering. And as a result of extreme clustering, you'll have like droplets occupying less than three-dimensional space. So they'll be occupying fractal dimension. So that is the basic story about caustics. And you need a lot of them, lot of caustics to happen at very, very rapid rate for you to get rain. So that's why caustics are very crucial for rainfall. So this is basically like to say that a lot of the world is covered by clouds at a given time, but a very small minority of them will rain. So caustics is happening at the right rate only in a very small minority of clouds. And it's worth spending a minute on this old problem of droplet growth bottleneck. So like we know that little droplets in a cloud, they can grow till about 10 micron in size by just diffusion of water vapor in the supersaturated environment. There's diffusion of water vapor and these things grow to about 10 micron. And after they become 50 or 100 microns, gravity takes over. And if you have a few large droplets who are 50 to 100, these then can fall faster than the others and collect more and more droplets. And for this to happen, you need like high levels of clustering to actually even reach this lucky droplet. So you need about 1 in a million lucky drop, which will then collect other droplets and become raindrops. So for this, you need a high level of clustering. So this is a definition I'm going to use. I'm going to pretend that the droplets can be described by a velocity field V. So U will be the flow velocity field and V will be the droplet velocity field. If you can define them by a velocity field, then we will ask del dot V, we'll find out where del dot V is less than 0. And wherever del dot V is less than 0, that means more droplets are coming into this region than going out. So you're getting clustering. So clustering corresponds to del dot V less than 0. Whether we can treat it as a field itself is another question. When I say that droplets are in a field, I'm saying something artificial. So like it's like saying I'm looking at traffic on a road and I'm saying a location X on the road has a velocity V. That's not true, right? Like each particle has its own velocity or each vehicle has its own velocity. So I'm attributing a velocity to a spatial location and a time, which is kind of artificial. But in turbulence, when there's a large number of small droplets, you can very often get away with treating it as a field. And this is a field to particle question that I want to keep returning to and find out like when we can treat it as a field and when we cannot. So like right now we're treating it as a field and we'll see when we cannot. Okay, so the middle part, like how it grew from 10 to 50, the answer is usually given as turbulence and the answer is usually given as, oh, there are these vertical regions and droplets are getting centrifuged out of the vertical regions. So they're voiding large spaces of the flow and they're concentrating in small spaces of the flow. So this is automatically clustering. So like, yes, this is clustering, but is it extreme clustering? Is it caustics? Is it that they're actually dashing on each other? This is a question that's not answered at all. And if you do like basic back of the envelope calculations, you will see that that doesn't give you, I mean, just this kind of voiding of vortices doesn't give you the complete answer. So like in this talk today, we'll be using the Navier-Stokes equations for the flow. So we're just using standard Navier-Stokes equations. We're pretending that the cloud is in turbulence by itself and it's not getting affected by the particles. That's for today's talk. Of course, it is getting affected by the particles. And the Reynolds number of the flow is very, very, very large, where U is a basic velocity scale in the cloud, L is the length scale of the cloud, very big, and nu is the kinematic viscosity. Then you look at particles embedded in this, and we say these particles are pushed around by the flow, but the flow is not pushed around by the particles. So like we take the simplest thing, which is the Gatignon-Maxi-Rayleigh equation, and we are using a baby version of the Gatignon-Maxi-Rayleigh equation, which is just given by this. And here I've written a subscript I, which means I'm talking about each droplet as an individual. So like I could think of them all having a field velocity V, or I could think of them having an individual. The way this one is written is in terms of them being individuals. And each of them has a Stokes number, which is a particle response time to the flow time scale. It's a non-dimensional number, which is a function of time because these droplets are growing. So, sorry, I left out a minus sign. Oh, okay. Minus. Yeah, so, okay. And the particle Reynolds number, which is V minus U, that means the relative velocity times the tiny radius of the particle divided by kinematic viscosity is much less than 1. So like the Stokes number is the measure of inertia of this particle. So these are the things we will follow. So yeah, so this talk is going to be about what happens here and what happens here, and what is here and here. So like here is where Q is less than 0, where Q is the Okubo-wise parameter. So it's basically a measure of a scalar measure of the vorticity minus scalar measure of the strain squared. And so wherever Q is greater than 0, what happened? I've interchanged these two. Q should be greater than 0 there. Wherever Q is greater than 0, you have a vortical region, and wherever Q is less than 0, you have a strain region. So sorry about this sign exchange. So like we're going to ask the question separately about the region where there's vorticity and the region where there's high strain. We already saw the movie where all droplets are pushed out of these vertical regions and collect in these regions of high strain. So then if you write a field equation for very small Stokes, this is what Sapsis and Haller and others did. You can actually write the field instead of VI, and you can write for small Stokes a V in terms of the U alone. And when you do that, you can actually derive this condition which says del dot V, which is the quantity we're interested in, is proportional to Stokes times Q. So like when Q is greater than 0, vertical region, it gets pushed out, and when Q is less than 0, it gets sucked in. So like you're getting this basic answer that it gets sucked into strained regions. But then this never gives us the opportunity for del dot V to become minus infinity. And for extreme clustering, del dot V it's not enough if it's less than 0, it has to be minus infinity. That's when caustics occur, that's when collisions occur. So del dot V should go to minus infinity, and we can actually get del dot V going to minus infinity when Stokes is small and Q is finite. So this thing is not quite correct in caustics regions, which points to the basic thing that whenever you have caustics, namely this, you cannot think of it as a field. So the field description fails at every collision. So, and unless you have so millions and millions of droplets have to collide to make one raindrop. So like if you have 10 micron droplets, 1 million of them have to join together to make a 1 millimeter raindrop. So you need these collisions, you need caustics. So like we're first going to ask what is going to happen here in the strain region where Q is less than 0. So in this region, we are going to talk about actual 2D turbulence, and we are going to talk about caustics without collisions in a field. So in other words, we are actually like trying to find how caustics happen by a clever method. And I'll tell you what the clever method is. The clever method basically is that you write this quantity Z as Stokes times grad V, and this quantity A as Stokes times grad U. So once you define these two quantities, you can see that when the trace of this matrix Z goes to minus infinity, you basically have del dot V going to minus infinity. Del dot V is nothing but the trace of this quantity Z. So like we have to write equations for this Z equation, pretend it's a field, and go and check where it diverges. So the divergence del dot V itself diverges. And when that happens, you have caustics. So we're basically going to look at it by this clever method. And the reason it's clever is the following. I'll come to that. But before that, like this is the Maxi-Rayleigh where we've added this other term for allowing for finitely dense particles. And this is the extra term which comes in the Z equation by accounting for finitely dense particles. So for the very infinitely heavy particle limit, this equation was already well known, but we've written this equation newly for finitely dense. We've just extended that. So as far as the equation is concerned, like if you're treating a heavy particle, that equation was already known. So now we just have to keep looking for trace of Z. So what we can do now is the following. Take like a big flow, take a few particles in it or a few droplets in it, just follow those droplets. You don't have to follow, like you don't have to actually count the number of collisions. That would be impossible. If you have quadrillion droplets and then you have to count each one's collision, that's going to be impossible. Whereas like now you're starting with a finite number of particles, finite number of droplets, large but finite, and you're following each droplet's neighborhood, and you're asking if del dot V is going to minus infinity in its neighborhood. So because you're doing this clever thing, you can actually attain caustics by treating it as a field and with a finite number of particles which you're actually following. So like although it's a field, you're following a few particles. That's how we decided to do this. And once a caustic occurs, you cannot call it a field anymore. So that particle has to be removed artificially from the simulation and something else has to be done to reinitialize. So yeah, this is a summary of the results that you get with this method. So delta, as you saw in the previous thing, is the measure of the, it's basically proportional to del dot V. So when delta goes to minus infinity, you're getting caustics, right? So then this you can see is sharply going down for a large number of particles, and zero is the caustics time. So very, very soon after this, you'll actually get it going to minus infinity. So delta goes to minus infinity for caustics particles. And these are all individual particle traces whose delta went to minus infinity. So like we've done this for 3 kinds of density ratios. This is like almost neutrally buoyant, and this is like infinitely heavy. So all the blue dots are particles which have gone through caustics at a particular Stokes number, but you can repeat it for other Stokes numbers. So like there's so many collisions which have happened, and you can see where those collisions happened. So that's basically something you get from just looking at the extreme clustering data where del dot Z went to minus infinity. Trace of Z went to minus infinity. Now, we're asking, like, are these in strain regions or vortical regions, right? And we were focusing right now on strain regions where this quantity is negative. So, like, we look at what these particles do, like whether they experience strain before they do caustics. So, the basic moral is things centrifuge out of vortices and then immediately they become raindrops. So we are showing that that's not the whole story and that cannot describe the whole thing. So there's more physics to it than just centrifuging out, going to a strain region and becoming a raindrop. So we are asking what kind of strain regions are these things exploring before they become caustics. And this is kind of the average. So they're experiencing some very high strain before going to lower strain and becoming caustic. So somewhere in their history, they have to experience very high strain. So that's a necessary condition for caustics formation as we see it. And now we see that there's more to it. There are, in these things, there are caustics particles which are given like this. There are avoiders which never ever go into high strain regions. So if a particle never went sampled high strain, it will never become a caustic. So forget about it. And whereas there are particles which experience high strain but still don't do caustics. So like, we're asking, is this just a sufficient condition that if you experience a high strain, you're going to go to caustics? Like if you reach a saddle point, are you going to experience caustics? So we're going to answer in the negative, and I'll explain why. So basically, we are doing these things where we distinguish between particles who have all experienced high strain, but some of them have become survivors. They never went to caustics, and some of them are caustics. And then like we ask what happens to those guys. So this is a picture of the survivors, and this is a picture of the caustics. So the dashed lines are the survivors, and these lines are caustics. So although they experience similar strain, like both of them seem to be going qualitatively through similar strain, there is some difference here. Like the non-caustics, the survivor particles go through like a very small strain before going deeply into this, and that has some meaning. But basically you see that there are some which just recover and never become caustics. And we've shown that there's one fundamental difference between these guys. The fundamental difference is, like, if you look at the strain, local strain, and you ask like how are these particles aligned, you will see that most of the caustics particles are aligned in the compressional strain direction, and the survivor particles are aligned in the extensional strain direction. So just being in strain is not enough. If you're aligned in the extensional strain, what's going to happen is that two of you will be here and here, and this one will race out, and this one will never be able to catch up with it, and you won't get caustics. Whereas if you're in compressional strain, this one will race in and catch up and collide against that. So that's basically the moral. Like, if you have a compressional strain, you have caustics. If you have extensional strain, even if the strain is very, very big, you do not have caustics. And because you're in this kind of thing where you're racing away from your follower, you're actually like, there's many, many characteristics in which you can distinguish these particles which will never become raindrops. So the point is that those things have like very, very low curvature. So they're basically going in straight lines, whereas the things which are caustics are going through high curvature. So that means they're going through wiggly lines. And this thing is no longer true. So when we write down this quantity cos theta equal to V dot E minus, so basically how aligned are you with the compressional direction? We've shown that quantity here. And you see that in the history, the caustics particles are all aligned in the compressional direction, whereas the survivor particles are all aligned in the orthogonal direction practically. And later in their history, it doesn't make very much difference where they're aligned, but already like at this point, well before caustics, it's been determined whether you're going to be a survivor or a caustics particle. So this is basically the summary of these findings. So till now it was just said that, oh, you go through turbulence, you go through high strain and you become caustics, and we found ways to distinguish in their history itself whether they're going to become caustics or not. And this is just a summary of that thing. So whenever you have better alignment with the compressional strain, you spend a lot of time in the strain region and you go through a very curved path. Whereas if you're a survivor particle, you spend only very short time and you race past that region, and so you never become caustics. So like, I think I'll skip the next part because I've run out of time. We can go straight to questions. Yeah, so this is the group right now, and this is the talk I wanted to give. Thanks for your attention.
Thanks, Rama, for the great talk.
Divergence V less than 0 is a signature of clustering.
Correct.
Why are you calling it also signature of caustics?
No, I'm not. I'm distinguishing between, sorry if I didn't make this clear. Del dot V less than 0 is clustering. Del dot V going to minus infinity is caustics. So caustics is equal to extreme clustering. So they basically like, actually we have other simulations where a bunch of these droplets go on to, planar or other geometries where they're occupying 0 volume. So del dot V is actually minus infinity for these point-like particles.
Yes, but this is to my mind, this is an empirical question that, like, it's not obvious from the definition.
What is not?
To show that divergence, I mean, even if show that means we are colliding more or non-field velocities.
No, by definition, if you're like going to a place where del dot V is minus infinity, you're reaching a place where you have enormous velocity jumps for zero distance. That's what del dot V minus infinity means. And if there even a slight component is pointing in that direction, then it's caustics. It's technically caustics. It's actually a technical definition of caustics.
Maybe just to follow up on that, it's not obvious to me that you need, like, why do you need caustics to get large drops? Like if you had del dot V smaller than zero for long enough, you would create as high a density of particles as you want in principle.
Yeah, so the thing is just having a high density of particles, if they're not touching each other, they're never going to collide and coalesce. So you'll never get a raindrop.
In reality, they have some size.
Okay. So you're right. Like technically, I can actually have them merely touching each other and then like coalescing, although their centers were not at the same place. But those kind of not collisions, but yeah, collisions due to the finite size, those are way, way, way smaller in number than these. We've actually shown that, like, you don't have a hope in hell if this doesn't happen. So just, things slowly coming towards each other and gently touching each other, that's like very rare. Like you just don't have enough of them. I mean, by orders of magnitude. But good question.
So do we know if these particles are electrically neutral or how would it change if I were to put a charge on one of these particles?
Kroor can answer that. Yeah, it's not easy. We just pretended that they don't have charge. But typically, like, I mean, as far as I can see, like charges are supposed to collect in one place. So how that happens, that they are, don't repel each other, that's an higher level question. So like people come up with interesting models, like, everybody is plus, 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 plus. And then you have one minus here and here is some plus, and that's how they attract. So yeah, there's very complicated models which are being proposed, which I don't know about.
Yeah, this is much more of a clarification. I was looking at the streamlines and can we go to that slide? I was just thinking along y-axis, I see extreme convergences and possibility of
Where this slide?
Maybe next one. Yeah, this one. Along y-axis, I see possibility of collision, but along x-axis, I see flow is diverging. And
yes.
So won't, in kind of very crude sense, won't the particle escape the plane and go in some other plane if they were pushed too much and may never reach the caustics condition of?
Yeah. So the point is you have to repeat this exercise in 3D to guess. Like we've been doing some 3D simulations and we are getting more or less these answers. So in the 3D, you'll have like one direction which is compressing and two extending, or the other way around. Two compressing and one extending. Yes. And the basic thing is similar in there as well, but you're right that they have more escape routes. So like we won't go by numbers and things that we get over here.
I see. But if it was 1D problem, then this is guaranteed that caustics will lead to growth of a droplet. If this was 1D.
If this is all in 1D, you're living in 1D.
Yeah.
Okay.
I'm just thinking, looking at this picture, I thought maybe the particle would want to escape and do the survivor all the time. I got that sense. Maybe I missed the point. Yeah.
Okay. So like basically if you're somewhere here, and you're trying to escape, but before you reach there, you have chances of colliding because you're slower there and faster here. So like you can catch up and collide. So yeah.
Thank you. Thank you for this nice talk. My question is about the particles. Do you treat them as solids?
Yeah, we are pretending they're just spheres. And for very small droplets, that's a very good pretense.
Okay, so
because the surface tension wins over everything else. And they're actually like perfectly spherical.
So then this result extends to ice particles as well.
For tiny ice particles, yes, but if you have larger ice particles, that changes the game completely. So like you do get like enormous departures from sphericity, and ice particles, there's no need for them to be spherical at any size. And these departures make like a huge difference to the way they collide and the way they move. So as a simple example, we've shown that if you have like a little drop and there's no turbulence, but a little spherical object is falling down, it falls vertical. But if you have like a funny shaped object, it can fall, it can explore much more and collide much more. Other things can happen. So yeah.
Thank you.
I'm just going back to the 2D, 3D thing. Does it make a difference that the turbulent cascade is upwards in 2D and downwards in 3D?
No. That shouldn't make a difference. That's my guess, because these droplets, their time scale is so short compared to Kolmogorov time scale. So like, whether you're going upwards or downwards comes out of, many, many, many Kolmogorov time scales, before which many of these events, caustics events, have happened. So they just see the turbulence instantaneously and they don't particularly care. For them, it's like a static frozen turbulence at any given time.
Very nice talk. I'm just wondering that since caustics occupy a very small volume of the whole thing, is there a measure of how many particles will do this? And so how important is the process?
Okay, so like, we'd like to believe that this process is crucial.
No, that's fine.
Like he asked whether without it we can make drops. So we need that. So what are you saying, 1 hour strokes? Yeah, that's if you use those models, like which may or may not be correct.
Okay. I mean, it will be that there will be, if you wait long enough, all particles will go through.
Correct. But in clouds, you go from 10 microns to rain in 10 minutes. So you cannot wait long enough. Otherwise, the cloud itself will disappear. So nothing is in steady state there. Yeah.
All right. Thanks.
So when I was in grad school, I think the state of the art was that we didn't actually know how rain formed because all the models took way too long. Is that still true, or is this solving that?
I couldn't hear your first sentence.
Sorry, it used to be the case that you could say we don't know how rain forms because all our models say it takes too long. Has this solved that problem? Can we say the caustics give us a timescale that's consistent with observations?
No, we haven't solved the problem numerically or quantitatively. We're just providing a mechanism and showing like how caustics can happen. So yeah, lots more needs to be done before that problem is solved or explained. We have some hand-waving calculations, like we made this calculation about how many caustics will happen so that you have a 1 in a million lucky drop. And first of all, 1 in a million is just a number pulled out of a hat. It's not a real number. But for that, we showed that you need a Reynolds number of at least 1 million for it to happen really fast. So you can make those estimates, but that's not solving the problem.
I have a question. So in this plot, the first one, you showed Q as a function of time, right? But your analysis kind of showed that strain rate by itself doesn't tell you whether you're going to go to caustics. So do you want to define a new kind of a diagnostic which takes into account the compression and not just...
Yeah, so that's this diagnostic, the cos theta.
Okay.
So we can show cos theta as a function of time, which I didn't bring here today, but yeah, that's so like strain along with the cos theta is the diagnostic. So whether we are aligned in the right direction or not.
Okay, yeah, thank you.
So you see in that next plot, we'd actually shown this cos theta thing. Oops. Yeah. So we just shown the statistics of the cos theta for survivor particles and caustics particles. So you see like there's a distinct difference in alignment.
Yeah.
Nothing is perfect. It's all statistical, but.
Yeah, that sounds good. Vishal, did you have a question?
wondering at what frequency would you need observations from real cloud or
To actually measure
yes,
caustics?
That's actually asking the same question I think Marty asked, but in a different sense. What would be the least count on instrument that you would require?
Okay, so people till now have only measured it indirectly. So like you measure the droplet size distribution at T1 and T2. And when you have a bigger size distribution, you say that, oh, so many caustics have occurred. That's only like, yeah, indirect, a bulk kind of thing. So whereas like it would be nice to actually see like caustics, whether they're going through compression, expand. I don't even know how you would do an experiment. You can't do it in a real cloud. You'll have to design a baby saddle point flow and then do this. You could, I guess. Yeah, because we've ignored a lot of physics of the near collision dynamics and such. So it will be very worth it to do those experiments.
Thanks.
Okay, let's thank Rama again
Thank you.
for the great talk.